Welcome to CP325 Embedded Systems Laboratory. Embedded Systems Laboratory is a 1 credit hour course, co-requisite with a 3 credit hour course CP323 Introduction to Embedded Computer Systems. CP325 is required for all students within ECE department, for students in electrical engineering, computer engineering, and cybersecurity engineering programs. Students meet twice a week, and each session is 80 minutes long. In this laboratory course, students gain considerable experience working with modern software development environments and embedded hardware platforms to solve practical problems. Through laboratory modules, students learn how to develop programs for embedded systems in assembly language and C or C++, how to debug and test embedded systems, and how to interface outside world through I/O peripherals such as parallel ports, timers, serial communication interfaces, analog to digital and digital to analog converters, LCD controllers, or direct memory access controllers. Embedded Systems Laboratory is located in Engineering Building Room 106. 106 is a closed classroom access with charger cards. The card reader is available near the front door. Students enrolled in the course are allowed to access the room during normal building operating hours. Notice here at the entrance signs that inform students about room policies. No food or drinks are allowed, and general safety information. Space dedicated to this room is approximately 520 square feet, and it accommodates a course instructor with up to 12 students. Inside the room near the front door, a fire extinguisher is available. The UH Office of Environmental Health and Safety and the ECE Lab Manager check and certify the safety equipment. Students must strictly comply with all lab policies outlined in the CP325 course syllabus, including lab access, general safety rules, handling emergency situations, laboratory conduct, handling and removing equipment, working on assignments, and submission of assignments. These policies are discussed during the first laboratory session, and students are required to sign a document acknowledging their commitment to following these rules. Inside the laboratory, an instructional podium with a computer, recording equipment, and projector is available. It allows instructors to deliver lectures, record them, and communicate with remote students. A whiteboard is also available for instruction. Inside the lab, 12 workplaces are available. Each workplace includes a workstation running Windows 10, oscilloscope, and 2 embedded development kits. The workstation is loaded with Texas Instruments Code Composer as a software development environment, MATLAB, and a suite of Microsoft Office tools. The first embedded development kit is available in the laboratory only. It includes an MSP430 experimenter board, a JTAG debugger, a Bluetooth modem, and a collection of sensors, including a 3D accelerometer, joystick, and others. The MSP430 experimenter board shown here includes 2 MSP430 microcontrollers, MSP430F4618 and MSP430F2013. In addition, the board includes an LCD display, a buzzer, a collection of switches and LEDs, and a microphone. The second development kit is given to every student enrolled in this course. Students take this kit with them. This kit includes an MSP430 launchpad development board with a USB cable, a USB to serial TTL cable, and an accelerometer with a set of color-coded wires. Students are required to return these functional and complete laboratory kits before the end of the semester to their TA. The laboratory is organized in modules, 11 modules, and final weeks are devoted to projects. The first module covers Introduction to Code Composer and Software Documentation. Laboratory 2 covers numerical systems and data types. Third laboratory deals with digital I/O ports, introduces experimental boards, and debugging. Laboratories 4 and 5 are devoted to assembly language programming. Laboratory 6 covers interrupts and C in assembly and also introduces MSP430 clock subsystem. Laboratory 7 deals with timers, namely watchdog timer, timer A, and timer B. Laboratory 8 covers serial communication interfaces and communication protocols, UART and SPI. Laboratory 9 deals with analog to digital conversion. Laboratory 10 deals with digital to analog conversion. Laboratory 11 introduces software reverse engineering in embedded systems. At the end of the course, students work on projects and they propose topic for their project. Each laboratory module includes a tutorial explaining main concepts taught in class and illustrating them through a number of demo programs that students are required to complete in lab or before the lab. Each laboratory includes one or more assignments that students are required to complete and demonstrate to their TA. TA typically gives a brief overview of demo programs, introduces assignments, and then guides students through completion of their assignments. The assignments are graded based on demonstrated functionality, quality of design, documentation, and students' ability to answer questions related to their design. In addition, 6 quizzes are taken in class and they test students' understanding of concepts demonstrated in the laboratory modules. Embedded Systems Laboratory covers 2 A-bit outcomes, namely Outcome 1 and 6. Outcome 1 defined as an ability to identify, formulate, and solve complex engineering problems by applying principles of engineering science and mathematics. To cover this outcome, Laboratory 9 is used. In this laboratory, students learn how to develop a program that interfaces an inertial sensor using an analog to digital converter. They apply principles of engineering to write the program and mathematics to derive measurable quantities from sensor transfer functions. The data is converted into force and then communicated via serial communication interface. Outcome 6 is defined as an ability to develop and conduct appropriate experimentation, analyze and interpret data, and use engineering judgment to draw conclusions. To cover this outcome, we use Laboratory 5. In this lab, students develop software-only and hardware-accelerated implementations of a particular computing task. They conduct performance measurement experiments and compare performance of the candidate implementations. With this, I conclude presentation. Thank you.